Answers are online. Yeah. They uploaded all the tutorial questions and answers before they hid everything. I'll send them if you want. It's pretty right, not that difficult anyway.
How are you? You've all gone quiet. I'm not ready yet. Right, okay, let us continue. So yesterday was a very gentle start, trying to remind you of what this course is about and where we're going. Let me just remind you again, just to tell you where we're going to go today. This course is really all about kinetics, or about energy in chemical reactions, from a theoretical point of view. Peter Gorry will follow on from my course and will give you a completely opposite viewpoint from the view of an experimentalist, and it will all be about the machines and molecular machines to actually study some of these reactions. Now, most of what I'm going to talk about today is encapsulated in about 3 or 4 Nobel Prizes in the 1960s and 1970s. One particular one, by Michael Polanyi, of course, was a Manchester graduate and did some of his work here. So what we're going to talk about in particular is really very, very pertinent to what the type of chemistry that was probably done quite a while ago, but it underpins all of modern chemistry, as you might imagine. Now, it started talking about the Born-Oppenheimer approximation. Now, this is nothing new. In fact, most of this course should be nothing really terribly new to you. It should all just be building on known concepts. The idea of the Born-Oppenheimer approximation is that we can understand molecules, or the energies of molecules, in terms of 2 separate entities. The first, the energy of the electronic system, the electrons. And that gives you the potential energy surface that you already know about. The other half of the story is the energy that is present in vibrations, rotations, translations within a molecule or a molecular system. And this course really is about how do we join the 2 together. Now, the Born-Oppenheimer approximation splits them up, and it very nicely splits them up in terms of 2 Schrödinger equations, 2 quantum equations, which each have their own solutions. So the nuclear terms will give you solutions such as the harmonic oscillator, the rigid rotor model, and the particle in the box model for translations. And at the end of the day, the most important equation that's going to come out of all of this is something you studied with Professor Whitehead, and that is the total energy is the electronic energy. Okay, well, that's the solution of the Schrödinger equation, that's the potential energy part. But then it's these other things, E translation, E vibration, and E rotation. And this is a very important equation. The fact that we can separate them into these different components will allow us to actually solve and get rate constants from some very, very basic principles. In fact, from the statistical mechanics equations that you already learnt last time. Now, in order for us to progress, we have to start to just understand a little bit about potential energy surfaces. I introduced you last time to the concept of maxima and minima on a potential energy surface, and as you're all aware, there are 3n-7 coordinates. So we finished last time when we were looking at the water molecule, because that's a very simple 3-atom system. We're only going to study 3-atom systems for most of this course. We've got oxygen and 2 hydrogens. Therefore, we've got 3 coordinates. 3 coordinates means that we have 3 dimensions to our potential energy surface, plus a 4th dimension, which is the potential energy. So we typically might draw some of these dimensions. We always draw the vertical axis to be the potential energy, and then we might have some x and y axes, or some axes on the plane here, which are the coordinates of your molecule. It tells you how does the energy change as I change the shape of the molecule. And the most important shape of a potential energy surface is that maybe of a reactant, that of an intermediate in a reaction, or a product in a reactant. And they all have this characteristic well shape. They're always at a minimum on the potential energy. The minimum point right in the middle there, that coordinate that shape of the molecule is what you would refer to as the equilibrium structure. And as you deviate from that equilibrium structure, we'll always go up in energy. And that's a characteristic of a minimum energy structure of a reactant or a product. And we can see that for this water molecule, and we looked at it in terms of an angle or one of the bond stretches. And they're just two coordinates that we decided to plot this diagram with. Now today, I want to talk a little bit about come back to that. I want to talk about this reaction. This is the one we started to study last year in Chem 20712. Now, there are some fourth years here who haven't done that course. I've been nicely informed. So I'll just take a little time just to get us all reacquainted with what we're talking about. Now, we're interested in this course in triatomic reactions. That's 3 atoms only reacting. And the simplest system which has been studied is that of a hydrogen atom reacting with a hydrogen molecule. Now we should immediately be able to tell that that results in 3 coordinates. If you look at that chemical reaction and we draw out our molecule, we have H plus H2. The system always conforms to this shape here. We have a distance between a first hydrogen and a middle hydrogen of R2, and a distance between the other 2 hydrogens of H1. Now there is of course a third coordinate. We've just seen that for water. There is an angle parameter. I think on my diagram here I call that angle gamma. Here, this angle here is gamma. Now we might ask, if we bend the system here, what might happen to the shape of the potential energy surface? I'll go back out again. What might happen to the shape of the potential energy surface? Well, we know that the shape of the potential energy surface starts out with a hydrogen atom at distance and a hydrogen molecule. So that's going to be nice and stable. The hydrogen molecule is stable, the hydrogen atom is stable. They're very nicely stable at a long distance. But as you bring the hydrogen towards the hydrogen molecule, you'll go towards a transition state where the 3 hydrogens will now share the 3 electrons. And that will, of course, end up going uphill and forming this transition state at this symmetric HHH structure where R1 and R2, the distances between the hydrogens, are equal. And if we continue the reaction, we'll find that it's actually very symmetric, and it will go back down to hydrogen plus a hydrogen atom. Hydrogen molecule plus a hydrogen atom at the other side. Again, we could study that using very, very high level, in fact you could very high level computational methods, and you could plot this accurately. We could actually do the calculation and get the potential energy, so we could plot this curve very, very accurately and compare it with experiments, and you'll find that it is remarkably accurate. Remember that this is the Born-Oppenheimer approximation. There's a little clause in your notes about how accurate is the Born-Oppenheimer approximation. Well, the Born-Oppenheimer approximation, remember, assumes that electrons move around the nuclei, and the nuclei are very, very heavy, so that when an electron moves, the nuclei are probably going to stay where they are. And when a nucleus moves, the electrons are so light that they almost instantaneously take up their new positions or their new distributions. So it's all about nuclei moving slowly, electrons instantaneously reacting to where the protons go. Now, when is that likely to break down? When is this principle likely to break down? Well, if your nucleus and your electron, or your nucleus is very, very light, then that's the most likely situation for the Born-Oppenheimer approximation to break down. Because then, it's the most, for example, you've got a carbon nucleus where you've got 6, what's that going to be? That's going to be 6 twos, that's 12,000 times heavier than an electron. That's a massive amount compared to a hydrogen atom, which is only 2,000 times heavier than the proton in the middle, in the nucleus. So if the Born-Oppenheimer approximation is going to break down, it's going to break down for hydrogen. It's going to break down for a system like this. where you've got the lightest nucleus in chemistry. It turns out that if you do very, very clever, accurate calculations, not within the Born-Oppenheimer approximation, then the difference in the energy will be about 5 wave numbers. So, according to the notes, this is on page 4 of your notes, that's 0.00062 electron volts. 0.00062 electron volts. That's the error in the energy of a hydrogen molecule by not assuming the Born-Oppenheimer approximation. That could be a large amount of energy, but if you compare it with chemical energies, dissociation energies, or other types of chemically meaningful energy, I mean, a typical dissociation energy will be about 5 electron volts. So that's thousands times greater than the error in the Born-Oppenheimer approximation. And that is why, even for this very, very light system, the Born-Oppenheimer approximation is nearly always assumed. It's always assumed until about lecture 6 in my series, when we'll talk about tunneling. And somewhere in about lecture 5 or 6, we'll actually see where the Born-Oppenheimer approximation does break down, and you get hydrogen atoms doing this, moving around in space without any loss of energy at all. And that's when you start to get some interesting features. But this is all based on the Born-Oppenheimer approximation. It's all really accurate. You can see that actually the reaction gives a reaction barrier when you have 180 degrees, a collinear. And it's noticed the double L in collinear, that's not a spelling mistake. When you have all 3 hydrogen atoms reacting along a line, that gives you the lowest barrier to the reaction. So the lowest barrier to the reaction occurs when all 3 atoms are in a line. If you increase the angle between them, then the barrier goes up. You can see that the barrier goes up as I increase the bend from 180 degrees up to, what's this one here, 90 degrees. So the barrier will get more if the atoms are not attacking each other, not colliding along a line. And that allows us to basically say, well, in reality, H plus H2 will occur by the hydrogen atom collinearly attacking the other hydrogen molecule. And so we'll only consider the collinear case for the rest of this lecture series. And we're going to assume the same for other molecular reactions. We're also going to be looking at H plus F2. We're going to look at H plus F2 in a lot of detail. That's a very, very interesting reaction. You've got somebody who knows volcanoes. So let's have a look at H plus H2. This is where you've seen this diagram last year. And this is going to be the basis of our talk today. What do we need to know about H plus H2? Well, we've got 2 coordinates. We've got the distance between those 2 hydrogens is R2. And we've got the distance between the other 2 hydrogens, R1. So, what we need to do is, on my potential energy diagram, remember that this vertical axis here, our vertical axis here is the potential energy. And that is the shape of the potential energy surface. It looks like a cube where somebody's chiseled out a runoff. And we have to look at that cube and you say, well, which are the reactants? Where are the reactants in that cube? Which coordinates? So, what are the reactants? Well, we're going to have H plus H2. So for the reactants, we're going to have H plus H2. Okay. So, which bond length is short? Well, R1 is very, very short. And in the reactants, the R2 is going to be very, very long. So, on our diagram, where does that place our reactants? Well, that places our reactants there, I believe. Very short R1, but a very long R2. So on my diagram there, that will place our reactants. On the contour plot, which remember is taking the contours of all of these contours of higher and higher energy, we're going to start with a very, very short value of R1 and a very long value of R2. So I think I've done that. So R1 goes that way and R2 goes that way. I'll just try and draw those on in colour again. So that is R1. And that direction there is, oops, that is green, isn't it? On colour. That one is R2. And that one is R1. This is a contour plot. So again, we know that our reactants are going to be here. So our reactants there, you can do the same for the products. What are the products? The products are when you get H2 plus H. So there, you have a very short value of R2 and a very long value of R1. And our products will be over here. So our products, I'll just put them in the middle here, products will have H2, H. So we'll have a very, very short R1, very short R2, but a very long R1, R2. So please, there's no need to memorize these diagrams. There's no need to memorize them. Work it out. Very simple. What are the reactants? What are the products? Which is my distance? This might be A and B. This might be B and C, rather than R1 and R2. In fact, they will be later on in the course. Work out whereabouts the reactants and the products must be on our graph. It is, after all, just a graph of 2 coordinates. So now we have to interpret what's going on, don't we? So what are reactants? What do we know about the reactants? We know that they're the lowest energy. So we know on our point here, you can see that that's the lowest potential energy, can't you? Up here is very high energy. Up here is very, very high energy. I'll try and draw high energy in red. Red seems to be a good colour for high energy. Okay, that's high energy. So, the regions of high potential energy are going to be in red. They're going to be the regions where this H plus H2 system is not going to want to go. So where do they correspond to? Where do these regions of high... What does this region up here correspond to? That region up there, this one here. What does that correspond to? What shape of H plus H2 does that correspond to? No? A very compressed H plus H2. All the hydrogens are compressed as close together. And you notice how the distance R2 is very short, and the distance R2 is very short, and the distance R1 is very, very short. So this here corresponds to H, 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 like that, all on top of each other. And down at the bottom here, this is where they're all a long way away from each other. So clearly, that plot is quite simply telling you what does the molecule not want to do. It does not want to have very long bond distances, and it doesn't want to have all very short bond distances. It wants to have a H2 molecule and a H atom. And so the molecule itself is going to want to stay in these very, very stable orange regions here, the reactant and the product. And if you remember where we finished up last time, and I just mentioned earlier today, we know that they are the lowest energy that you can have. They are minima. These orange regions are very low energy. In fact, they are minima. Okay, the orange regions are minima. So you're walking in the hills. Here is a picture of the hills. Where would you walk to go from reactants to products? Would you walk up and over this mountain and back down to the other side? How many of you, quite a few of you, would want to do that just for fun? I personally would prefer to walk around the back of that mountain, around that valley, from round to the back, around to the side. And I think that's very important that you realise that's the way to go. I would want to go from reactants to products. I would want to go along the valley from reactants to products. So I would want to go along that valley. And can you see how these contours here are increasing energy? So this is the lowest energy route. The one in brown is what we call the minimum energy path, which is the lowest energy route. And the lowest energy route is where a molecule would ideally like to take. And that's where this course is going to deviate a little bit from last year now, because now we've covered the general idea of a potential energy surface. Now we want to start asking questions about, well, what can a molecule do? If you want to see a three-dimensional plot of this, there's an Excel spreadsheet from a practical from many years ago on the Web Blackboard site, so you can actually, we've done a calculation and plotted them all out, and you can see a 3D contour plot and play with it to show that it's quite real. So all this can be computed, and there is in fact, that data is on. And here's a nice summary page. Here's the summary of what we've drawn on this rocky looking slide on the left here. Key features. Which are the reactants? Which are the products? You'll notice that on my nice ideal picture on the left there, I've rotated this around. You notice where the origin here is at the top to match the three-dimensional shape on the left here. So what I've done is I've rotated that around so that the origin is now in the bottom left-hand corner. And that's the way in which we would normally represent this picture. Again, sometimes I think all the diagrams in your notes have the reactants on the bottom right, going to the products which are on the top left. But you might find textbooks that decide to go the other way. You have to think, what are the coordinates, and what are the coordinates saying? So just bear that in mind to work them out. And the most important point for the rest of the course is going to be, where is the transition state? And the transition state, X marks the spot. It is the highest energy point along that lowest energy path. Because that lowest energy path is not uniformly flat. It goes up and down in the shape of a reaction profile. Picture of that somewhere. There we go. So I'm going to take now that nice painted picture, and I'm going to take you on to a few more pages further on into your notes, quite a bit deeper into your notes, and we're going to come back to the bits in between as they come up later on in the course. So I've jumped to page 23 of your notes. And the reason I jumped to page 23 is because today it's logical for us now to pursue this picture, to pursue what's going on here. So we will be returning to the detail in between. So what do we know about this picture? Well, we know that the transition state is the red dot on this picture here. And notice now I've changed, instead of going from H plus H2, I've just called A, B and C atoms. Atoms A, B and C. And along that minimum energy path, that lowest energy pathway, the ideal route from reactants to products, we could actually take a cross-section. And the cross-section, because coming out of the page, this contour diagram, remember these contours depict the potential energy coming out of the page. If we take a cross-section along that route, the energy will go up and down, and the transition state is that highest point in the middle. So on the right we have our conventional picture that you see in all the normal chemistry textbooks, and on the left we have a depiction of the potential energy surface that we require to understand the reaction dynamics. Now the first thought experiment I want you to all try and think about now is, what does this minimum energy path mean? In terms of a chemical reaction, what's actually happening to the atoms? So where do we start? Well, let's have a look. This is RAB. RAB. So we start out at a very long distance at our reactants. It's a very long distance there, of the reactants. It's nice and stable, it's at a very low energy contour there, that's a very low energy region contour there. Very low energy there, that's our reactants. What happens along that brown minimum energy path? What is happening in the molecule? Well, you can see that for most of the first half of it, this distance RAB is getting shorter and shorter and shorter. Notice how, as we go along here towards the products, RAB gets shorter and shorter and shorter. So A approaches B. So what does that indicate? That indicates translational motion. That's translational motion of atom A approaching a BC molecule. And what do you notice about this first region of the potential energy surface along here? What do you notice about the BC molecule? What happens to the BC molecule for that first part of the reaction? Nothing. The bond length does not change. So you have atom A approaching BC and not a lot happens until you get quite close to the transition state, and then all the bond lengths just are nice and symmetric, and you notice that at the transition state we have A, B, C, and we have them equidistant. And you have them equidistant here. So RAB is the same as RBC at the transition state. It's symmetric. For the H plus H2 reaction, this reaction is nice and symmetric. What happens as we go towards the products? What goes out to the products? Well, then what's going to happen is that RAB is going to stay the same. It's now formed the H2 molecule. And what is going to happen now, C, like this distance BC, here, gets bigger and bigger and bigger. In other words, that's the same as saying, after we've gone through the transition state, we form a H2 molecule, and the other hydrogen atom recoils off. In fact, it's just like a game of billiards. We have three balls, too close together, one ball comes in, collides and reacts, and then the other end one flies off. All of the energy along that minimum energy path, everything in that reaction that we've discussed so far is translational motion. Therefore, it's all to do with translational energy. The faster that they collide would correspond to more translational or kinetic energy. So that very, very straight path is all about translational motion and translational energy. So if I said to you, explain to me what happened in a collinear chemical reaction where there was only translational energy, you would answer that question by drawing that diagram and saying that is the way in which the reaction would occur. It would take that trajectory, the brown trajectory, and along that brown trajectory the energy would go up to a transition state and back down again. That's a purely translational energy picture. Now obviously that's very nice, it's great, but what do we know about molecules? The first thing is we've got a hydrogen molecule here, and we know that molecules, or any molecule, must have some vibrational energy. So the next question is, how do we incorporate or draw a trajectory which now starts to incorporate some vibrational energy? What sort of trajectory will actually take place? This is very ideal. This is not what happens. This is very theoretical. What actually happens, well, is a bit more complicated, this one. There we go. Let's ask what's happening here. Again, think about the coordinates. Don't just blindly draw the diagram, think about the coordinates. And what do the coordinates tell us? RAB, our reactants, RAB, that distance there, that distance there. Well, RAB is going to, along that trajectory, in fact, let's draw it out for you. Let me draw it out for you. A red trajectory this time. Let's ask ourselves what's happening along that trajectory from reactants to products. So along this first part of the trajectory, on the way to the transition state, what's happening? RAB is getting shorter. Meanwhile, what's happening to the BC molecule, to the BC distance? Well, the BC distance here is changing, isn't it? It's oscillating. We go to shorter BC distance, longer BC distance, shorter BC distance. What's that corresponding to? That's BC distance getting longer, shorter, longer. That's a vibration. That's a classical vibration. So this initial period here, this initial period here, there, corresponds to, well, it corresponds to the A molecule translating, because the A molecule is still approaching the BC molecule. So we have A translating towards BC, and we have the BC molecule vibrating. So everybody see that. I'll go through that again because it's very important that there are two things going on. Remember that the AB distance is getting shorter. That means the A molecule is approaching the BC molecule, relatively speaking. And the BC molecule is getting a shorter bond length, a longer, shorter bond length. It's vibrating. It's going shorter, longer, shorter, whilst A is. So we can see how we've incorporated the vibrational energy onto that picture. The vibrational energy is simply is shown by the amount of vibrational amplitude. Obviously, if it's a lot of vibrational energy, we would expect this to vibrate a lot. Because remember that this is a well. Think about these contours. Think about the contours out here. As I go towards longer BC distance, the energy goes up, 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 up. And then down here, the energy goes up, 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 up. There's a well. So along this distance, along this coordinate here, we are actually vibrating with respect to potential energy. So our vibration is a very classical vibration. It's a very classical, getting longer, getting shorter. And classical vibrations for most larger molecules, actually, they are very classical, most vibrations in larger molecules. They're a quantum mechanical phenomenon, but when you get to reasonable sized molecules, they are starting to behave quite classically. At least statistically speaking. Now, what happens then at the transition state? Now, you'll notice that on this occasion, I've drawn the trajectory going through the transition state. Now, it's a very good question. Does the trajectory always have to go through the transition state? And this is a good question for later in the course when we discuss transition state theory, where transition state theory, on the surface of things, says, yes, all chemical reactions have to go through the transition state. But then you have to come to a definition of the word state, because that's where the key is. What we must be very careful of when you draw trajectories like this is we'll always draw them probably going through a transition structure. That's a single structure here. A single shape of the molecule, which we say is the transition structure. Okay, it's a single structure. Now, chemical reactions do not always have to go through the same transition structure. But they do have to go through the transition state. And the difference between the words is that transition state has many different structures. And in fact, on this diagram, the transition state would be any structure along this what we call a dividing surface. don't worry about that for this course. Please don't try and write that down and confuse yourselves. This is really just trying to fill in the gap for those who are following me very clearly. Transition structure and the transition state are actually slightly different things. So that trajectory will always have to pass through the green dotted line. It will always have to go through the transition state. But it doesn't always have to go through the red dot, the transition structure. Okay? That's just something that took years for me to understand. Now, what happens to the products? Can you work out what happens to the product region? What's happening here? Just to make sure we're all on the same wavelength. What's happening? Well, the BC distance is increasing. So we have here, we have C, the C molecule, the C atom, has translational energy. Okay? And what's happening to the BC distance? Sorry, the AB distance. The AB distance is getting longer, shorter, longer, shorter. So we have an AB molecular vibration. And that starts to make it look very interesting. Because what happens if I could change this trajectory slightly. I could give it slightly more kinetic energy. So I could have this reaction occurring with slightly more translational energy. What's going to happen if I give it slightly more translational energy? Imagine, do a thought experiment. If I now give atom A more translational energy, it means it will go faster in that direction. The same amount of vibration, or energy in BC, BC is vibrating. What's going to happen if I give it a lot of kinetic energy? What do you think might happen? Imagine yourself on a bobsled. There we go. On a bobsled, trying to go from one side, from the reactants over here to the products over here. What do you have to do? What can you imagine happens if you go too fast around the corner? You go up the corner and then you come back down it in a horrible, with a lot more energy than you ever intended. So you could end up, if you go too fast in this reaction, too much collision energy, you'll end up going up here maybe, and then down here. In fact, here's a little aside for you. The person who actually I talk a lot of this with is a professor at Bath called Professor Ian Williams. He's a physical organic chemist, and this is one of his. He's always been very, very interested in physical organic chemistry, chemical reactions, and transition states. It's actually one of his pet subjects is transition states of organic reactions, and looking at these things. Isn't it quite amazing that his daughter is Amy Williams, who loves bobsled riding around these sort of surfaces and taking the corners at the right speed. So there's always something out there. Unfortunately, she didn't take the chemistry apart. So where are we going to go from here? So now we've got the general idea. I think the idea I want you to take away is we've got translational energy coming in and translational energy going out. We've got vibrational energy of the BC molecule coming in and vibrational energy of the AB molecule going out. And we can run computer simulations of these and take the average of all the possible reactions with the right energy. So we could actually simulate this with the right amount of collision energy. So when you talk to Peter Gorry and he tells you about his molecular beams experiment, he'll be telling you about the velocity of these atoms. He'll be converting the velocity of the atoms into translational energies. And theoretically, you can convert those same energies into trajectories and work out what will happen to the products. And let's see what sort of very interesting things that turn up. Right, well, I just want to make sure we've dotted the I's and crossed the T's here. I go the right direction. I'll come back to those next time. Right. When do chemical reactions not occur? Chemical reactions do not occur when there is insufficient kinetic energy to get over the potential energy surface. So if I have I can go up and back down again. If I don't have enough translational energy, collision energy, then the chemical reaction will not occur. Tick, that's good. It all tallies up. What happens if we have lots and lots of vibrational energy? In fact, this is exactly the same. You should actually say not enough translational energy, doesn't it? You should actually say translational energy. But lots of vibrational energy. Okay, so that's a mistake on the slide. You can tell that because what's happened? We started out, we've got lots of vibration energy, but we've not got enough collision energy to quite get to the top of the barrier. And so what will happen is it'll come back and vibrate back, and it'll probably go back in the loop. So we need to have just enough translational energy to get over that barrier. We do need to have some translational energy, enough to get to the transition state, but not too much, and it doesn't really matter how much vibrational energy we've got. That's a very interesting question, and you'll see some of you might look at that and say, that's very interesting later on. So, let's move away from H plus H2. Let's look instead at the reaction between the fluorine atom and the H2 molecule. Now, what do we notice about this potential energy surface? The first thing you should notice about the potential energy surface is where is the transition state? Notice that this potential energy surface is not symmetric. So here are reactants. There are reactants, velvet and green. There are reactants over here, and there are products up here. And again, we have a minimum energy path. But notice how this time the contours are not evenly spaced. Notice how these contours are not now nice and symmetrical. So, on this case, I want you to look at where is the transition state. This is what's called an attractive potential energy surface. The word attractive, to me, is a very, very misleading term. It was actually used in the original experiments because of the mathematical formula that actually to describe this surface turned out that this really refers to being attracted to the reactant potential. I think in modern organic chemistry, we would definitely always say that this is an early transition state. And you can see why it's an early transition state. You can see that along the minimum energy path, if I could dot the minimum energy path, which would be here, this is the ideal lowest energy minimum path. This red dot of the transition state is early along that reaction path. It's early, it's nearer to the reactants than it is to the products. This actually corresponds to a potential energy surface that is going to look very, very much like this. Reactants and products. So, have you done Hammond's postulate yet in physical organic chemistry? Hammond's postulate yet? No? No hands? Oh good, because that'll be new in this course, because we actually come back to this quite again later on in the course when we try and put together a few of these concepts. Hammond's postulate is a very, very useful physical organic concept which says that if you have an early transition state, then you've probably got an exothermic reaction, or vice versa. The two go together. If you have an exothermic reaction, then you have an early transition state. The transition state is more reactant-like than it is product-like. We'll come back to that concept later on, but you can immediately see how that can occur just from the shape of this collinear reaction between F plus H2. So again, these are the high energy regions, low energy region, but notice here how the peak is actually much closer. If I was to draw this middle line as the centre, well, I'll draw it in dotted red. There we go, that's a dotted symmetric line. Notice how the transition state is early along that reaction coordinate. Now we've got a chemical reaction that's quite interesting, F plus H2. Let us react that with an ideal chemical reaction with just translational energy. Just for simplicity's sake at the moment. What might happen if I react that with just translational energy and just the right amount to go up and over the transition state? What's going to happen? What might happen to this chemical reaction? Well, let's follow. Just enough translational energy. So there's the translational energy. No vibration in the BC molecule. And where's it going to go? Now, imagine now you're bobsledding down that valley. What's going to happen? It's going to go up that wall, and then up that wall, and we're going to end up oscillating to our products. There's no way around it. There's practically no way around that. Very, very, unless you had exactly the right amount of kinetic energy just to turn that corner perfectly. It is possible, theoretically, that you could do that. It is possible that you could do that with just the right amount of translational energy. But it's more likely that you're going to have just slightly too much translational energy and you're going to end up vibrating. You're going to end up vibrating. I'm going to come back to what this little diagram means in a minute. But think about this. You start out with too much translational energy and you have no choice but to end up with vibrationally active products. Okay? Unless you've got just exactly the right amount of kinetic energy to turn the corner, it's possible then you might not. But the odds are on against you there, and this chemical reaction is going to excite the products. What's also going to happen? How are you going to imagine now you're trying to do this with a ball in a fairground exercise? Try imagine a fairground exercise. This time you have to start it off vibrating. It's not very clear. What colour have I got left? Blue. I've got blue here. There we go. Blue. Right, start it off vibrating. Can you get it through the red dot and down towards products, down that valley? Is it possible, do you think? Ooh, it's going to be very close, very difficult indeed. So if you actually have a lot of vibrational energy in your reactants, then you're not going to be able to make this reaction occur. Look, what's going to happen? It's going to bounce off that wall and then back again. If you have too much vibrational energy. It might just be possible if you have just the right amount of vibrational energy, you might just be able to get it to go round the corner, and then maybe you will be able to make that reaction occur. Again, try and think this is a thought experiment. You can quantitatively do these experiments by doing simulations. But in this course, we're really mainly interested in asking ourselves about, can we describe the chemical dynamics on potential energy surface? And this is what would happen with an attractive potential energy surface. At the beginning of next time, I'll revise what happens on the opposite of that. A repulsive potential energy surface, the opposite. Very simple, ideal place to start the next lecture by way of